Blanchet taking over for the third lecture, and he'll be doing today and tomorrow.
Okay, thanks very much. Well, thank you. This is your last lecture of today, so I bet you are tired. I'm not going to say that I'm going to make it entertaining, because if I fail, then I'm going to look bad. But I'll say that if I see somebody sleeping, I'm going to applaud or something. So that way, I should get this done. Okay, so I'm going to talk about distributionally robust optimization. This lecture is based on, well, the two lectures are based on these three papers that you can access online. I'm going to just have them there in case you kind of want to take a picture or write the name, the numbers there, and I'll just, take this, a couple of minutes to say. So this is an area that I started working in 2016, and we have been developing several results, duality results, statistical results, and I'm going to talk about these results, including connections to estimators that you probably have covered earlier. And one of the things that you have been discussing minimax estimation, and there will be a minimax thing going on here, and I'm going to explain why this is not the same minimax as the minimax. Too many minimaxes. And there is also the word robust, and you're going to think that these are robust estimators, and you're going to later learn that these are really not robust estimators in the same sense that the statisticians think as a robust estimator. That's actually the word robust is very well justified. It's just not, turns out not to be the same as what is done in statistics. Peter Hoover and this kind of thing. It's not. We'll talk about that. And this is optimization conscious econometrics. So I'm going to talk about a lot of optimization and duality and stuff like that, and econometrics, so also a lot of statistics. So this has given me a chance for you to kind of take a picture, and now I'm going to move on. So I'm going to take the point of view that distributionally robust optimization the goal is to make a decision, so it's decision making under uncertainty, and I'll frame it in such a way that I stay at the beginning away from the statistical question. I'll then come back to it. And I'm going to talk about some applications. I will tell you some surprising things that I've seen in experiments, and I'm not an econometrician, so I'm just going to show you something. I think there are lots of people here that might be surprised about this, and some experiment that I think is kind of interesting. Then I'm going to talk about some properties of distribution and robust formulations and solutions, and then I'm going to talk about the statistics of these problems and formulations. And this is going to be kind of like a menu sampler of many things, and the next lecture I'm going to kind of go deeper in some of these topics. All right. So what's a typical sort of like decision making under uncertainty problem, like expected sort of like loss optimization? This is the simplest one that is justified, but by the decision theoretic approach of von Neumann and Morgenstern. You end up having some sort of utility, or in machine learning some loss, and you want to minimize the expected loss according to some parameter. There are other criteria that you can follow that are non-linear in the probability distribution, and I will talk about that stuff in the conference on Friday. But here I'm going to concentrate on the case where this is linear in the probability measure. And so in that typical setting, assuming that you know your probability distribution, it's very natural to try to make your decision according to this criterion. So you want to minimize the expected loss. And the ideal situation is that the randomness, the source of randomness, is known. Well, in practice, of course, you don't really have this situation unless you design the engineering system in such a way that you have the distribution, you access the distribution. You typically have a situation that is more like this. You collect samples from some population distribution. These samples might be correlated or might be independent. For the talk, you think that the samples are independent and identically distributed from the population, and we can talk about how to extend and what things actually work in that setting and what things do not work in that setting, etc. So to keep it simple, you have this data, and then you collect. Yeah.
What is psi? Is it in this thing?
Yeah. So this parameter throughout the rest of the talk, theta, is going to be the decision. So think of portfolio optimization. Theta is going to be a weights of portfolios. In fact, that's one of the examples I'm going to give. This is going to be, that's the random source of randomness. So notation is for expectation in the subscript is also always going to be the probability distribution I use for the source of randomness. And here there is, sometimes I'm going to say psi follows distribution pi or p or whatever, except when there is no confusion. And here it's okay because I'm infimizing. This cannot be random because I'm infimizing. So that's just the variable that I use to infimize. Okay? So that's kind of like the standard data-driven decision-making, paradigm. Now, what happens if the true distribution, and we are going to talk about what true means, but in general, true distribution means the distribution you face at the time of deployment. So think of, again, portfolio optimization. You are going to find what's the best portfolio that is going to maximize the performance, right? Maximize the performance, optimize the performance, right? So it could be maximizing utility or minimizing the negative of the utility, which is the same thing. And so you have this notion, true distribution that in the end is the distribution you face at the time of deployment. And distributionally robust optimization is designed in situations where the true distribution is different from the distribution that generates the data. So I'm going to show you an example that sort of kind of motivates the use of distributionally robust optimization. So this is a basic sort of portfolio optimization model. Is mean variance. I'm going to walk you through the setup. It's not really important that is mean variance. Mean variance is 1950s, 1954 Markowitz. Chicago, no? Chicago, Markowitz? No? Was it? No? Yes? Yes. Yes. Chicago is one of the heroes, right? So Chicago. So I thought, okay, let's do that one. You can see variance is not a linear function of the probability, right? Because it involves the expected value and that quantity squared. So what we do in optimization to make it a linear function. So yeah, let me show you. So the expected value. So portfolio, the portfolio selection problem is minimize the variance. Theta are your weights, X are the returns, and then minus this coefficient of risk aversion and the expected value of the return. Yes. Now this variance here, as a function of p, is not linear because the variance of anything is the expected value of that thing squared. This is linear. This is linear in p because this is just simply the sum over xi p xi. You see here the p appears linearly, right? But this part, when you take the expected value of x and then you square it, that thing is not linear. The probabilities will appear a square, right? This quantity square. So That's what I mean when I say linear. That is important because when I talk about DRO, I'm going to talk about linear programming, infinite dimensional linear programming. So let's just set the stage of what do I mean by linear, right? So this thing here, this thing is linear as far as P is concerned. Of course, it's not linear in X squared, but I don't care. What I care is about P. Okay, got it? Now, here, this is a very standard trick in optimization. You basically linearize. For an optimizer, you don't care. You can add as many variables as you want. Here, if I add this auxiliary variable alpha, when I minimize this function here, this doesn't depend on alpha. So the minimization problem here of this is the variance. So I can write the variance as something linear as long as I include this additional, variable, artificial variable. When I optimize first over alpha, this becomes variance. So that's why I can make this mean variance portfolio selection problem also of the form that I described earlier. So it's minimizing the expected value of something that is linear. This is my loss here. Okay? Now, as you move the coefficient of risk aversion, what happens is you have this, you draw this Pareto frontier, right? The more risk measured in terms of a statistical risk, the more return you are expected to have if you choose optimally, of course, right? So for every parameter of this eta, there is the best portfolio that trades the return with the variance. For this level of standard deviation, this is the best you can do with the return, right? And it kind of looks like concave. All right, so you in practice don't have the true distribution of the returns. That thing might not even exist in the sense that the distribution, there is no dead distribution because it will change maybe from time to time, right, at the time of execution. So what you can do is you can take the data, and this is my notation for the rest of the talk of, this is the empirical measure. So this is the distribution that is uniform on the data points. Let's assume that the distribution that generates the returns here is continuous, so there is no tie, so that is uniform really on the data set. And you can do fancier utilities. This story that I'm going to show to you is not going to change. So this is what you do in practice. In practice, there are lots of things that you have to do in practice to choose portfolios. You need to have additional information. Additional information also helps, like French FAMA and factors. Typically, the portfolios are very large, and you need to kind of do some sort of like dimension reduction. You want to estimate the covariance, and you want to have good covariance estimators. All of that stuff doesn't really change that much what I'm going to say. Okay, so I'm going to do it with a small number of assets, not that many assets. So many of the problems in high-dimensional statistics will not be present in my experiment. So the experiment is, what I did is I took, well, I didn't do it. It was Fan Zhang, who was a PhD student, who is now at Citadel, Chicago as well, no? Boy, I have so many connections to Chicago, it seems. And Karthik he's not in Chicago. He's in Singapore. He was a former postdoc. So what we did, this is an optimization paper. And when the student did this, I told him, no, you have to be careful. Do it again. And then eventually we're like, okay, well, this is what it is. We report it, and this, I'm going to show you what happens. So what we did is we look at 10 years of data. So a rolling window of 10 years. So that is from 1990 to 2000. The S&P 500, we pick 20 stocks at random. Those are the seeds, okay? 20 stocks at random to estimate in these 10 years of data according to sort of monthly investment. We collected these returns for these 20 stocks in these 10 years. We solved this problem this problem with these 20 stocks selected, right? 10 years, that's our empirical measure, solve this problem, and we get a strategy that we implement. And then that thing that we got, that strategy, that predicted a return, 1 month return, and predicted a standard deviation for that portfolio. We call that in sample, okay? And then what we do is we implement this strategy, and then we see what happens in the first month in January of 2000, okay? So we see what happens. We collect the return that was obtained and collect, the value of that return. And then we do it again for the next, this moving window, 10 years. We repeat the strategy. We keep, optimizing month after month after month until 2017 for these 20 stocks. If at some point between 2000 and 2017, one of these 20 stocks leaves the S&P 500, we pick another stock from the S&P 500 and we replace it, okay? So, and we continue. And then we did this 200 times for another 20 stocks, and another 20 stocks, and another 20 stocks. So we repeated this choice of the 20 stocks for 100 times. Is it clear what experiment, how we did the experiment?
This is the name estimator you showed us, it's not distributionally robust.
Yeah, I'm going to show you now what happens, right? So I'm going to show you plots that look at the in-sample estimation. When we average all of these runs, how the efficient frontier, so we do this, by the way, for all the values of this parameter, the risk aversion parameter, because we want to draw an efficient frontier. I want to draw an in-sample and an out-of-sample efficient frontier. That's what I want to show you. Yeah?
And just one question. So do you have a budget, or how are you implementing this strategy? Were you assuming that...
Oh, it's self-financing.
Self-financing?
Yes. Yeah.
So just the value of the portfolio?
Yes, because it's right. I mean, the norm, if you look at the optimization problem here, the weights add up to 1, so it's this constraint is just whatever is your budget. Yeah.
Yeah, so for the years starting from the first month of 2000 all the way up to 2017, do you have data for this period as well?
This is just based on this data from like Wharton. It's a very famous sort of database. You can download all of this data weekly. Yeah, we have all of this month. What do you mean? I don't look into the future. Is that what you're asking?
Well, the first bullet point says 1992, 2000s. I don't know
How to interpret that?
Right.
It means I pretend, of course, we are in 2024, so let's pretend I'm in 2000, and I have collected 10 years of data, and I implement, and then I, roll over, and then I get to see the future.
Right, okay, so you pretend that you don't see the data starting from 2000.
Yes.
And then you produce predictions.
Yes.
In the, and then you
Month by month, right.
You don't correct your predictions on the go with new data starting from 2000. Right?
Yeah, of course. I mean, every time in January, I keep a 10-year window rolling. This is also something is done in finance. You are not supposed to keep like data for from like 1900s, right? So you kind of I have this 10-year horizon that is my past window, and I keep it with me. I carry that 10-year window with me. Of course, by 2005, it's going to be back to 1995. Yeah. Okay? Clear? Yes.
Is there any restriction on the weights? Like you cannot go short, and can you short and can you stop? So for example, if there's an asset that's performing like really good, you put like a restriction on the way that you can
No.
on an asset. So
No.
no short.
Nothing
you can
funded.
Short and you can
Yeah.
that can do whatever.
Right.
Okay.
Right.
So the weights are larger than or equal to 0. I didn't see that restriction.
No. For this experiment, I did both. And what I'm showing, I think, is the case where it's greater or equal to 0. No. That's actually what I'm showing is this just the free. Yeah. So, okay. So this is the theoretical efficient frontier, right? it looks it has to be concave, as I said. And this is the in-sample definition frontier, and I have this parameter here that is going to play a role in the rest of the talk. This measures the risk, but it's not a statistical risk. It's model risk. And what happens is that, so this is a parameter I choose, a little bit like this coefficient of risk aversion. And as I move, this parameter, this parameter is combined with another formulation, which is the point of this lecture, that I haven't shown you. But that formulation basically introduces an agent that plays an adversarial game against the investor. And when I sort of introduce this artificial agent that plays a game against me, and then I, try to choose my decision, my portfolio selection that incorporates that agent, of course I get decision frontiers that are worst. As delta increases, I get, the curve moves down in sample, right? In sample, it looks like I'm doing stupid decisions because I'm kind of worrying about something that I shouldn't perhaps be worrying about. And so I create this, this inefficiency in sample. But out of sample, there is this very funny phenomenon that happens. I should have shown the dispersion. So it does have this tendency to go down. The standard deviation increases. And out of sample, you start getting something that is, less bang for the buck with your return out of sample. If you look at I'm going to enhance this size of the picture. But however, what is true is like, okay, you fix a coefficient of risk aversion, and you see that as you increase this delta parameter, you are actually getting better performance. So the performance actually flips. When you incorporate this model, this notion of model risk, your model is wrong, basically, you get better and better performance. And if you track there are two lines here. So this line here corresponds to an adversary that is designed using market information, not past information. I'm gonna teach you how to design this, and that's the point of the talk. So there will be an adversarial mechanism that in which the adversary I endow with properties, and these properties are based with the implied volatility. That's information about the expectations of the market in the future, not the past. When I do that, I get this a little extra better performance than not including the market information. And that's one thing. And the other thing is that if instead of plotting as a function of the standard deviation, I plot as a function of the model risk, I kind of get this more realistic sort of like concave curve. So this is the robust method, not informed by future market expectations, and this is the robust method informed by future market expectations. And so kind of the thing that I'm trying to pitch here is this empirical example illustrate that model error can, the fact that model error exists, maybe because non-stationarity is something, my flip stylized economic features that you might expect, in the data. And but a similar phenomenon happens in machine learning. And also another thing is that by looking at the market expectations right now, you can try to model that in the framework that I'm going to teach you. Now the same sort of flipping phenomenon happens in machine learning. This is a very famous example from the same thing happens now with much more advanced neural networks. You can attack also large language models, and the same thing that was found first in this at that time was a state-of-the-art network, and this group of of researchers. Ian Goodfellow, became really, really famous with this type of, in this example, this shows, a situation where you have a very, at that time, as I say, it was like a state-of-the-art neural network that was pretty good at classifying, and it was attacked with some a special type of attack. J is the gradient, is the loss. You look at the gradient of the loss. You take the sign. Theta is the parameters of the neural network. You add this noise. A human would not distinguish. This looks like a panda for a human, but now the machine is very, very certain that this becomes a gibbon. So these types of adversarial attacks lie at the heart of the types of attacks that I am going to explain in a minute, right? So this is an optimal transport adversarial attack, and optimal transport theory is designed in everything that I'm going to say. Now, distributionally robust optimization as a statistical tool. Okay, so this is another experiment. So this one is designed. So what we did was this is just simulated data. Okay, this is not real data. What we did was simulated 100 linear regression. Different independent realizations of the same model. That's what I mean by model. It just means it's the same model, simulated data, 100 different realizations, each containing data points. And we have different cases here. The case is a two-dimensional linear regression, so we are estimating a parameter that is two-dimensional. And we have different collinearity cases here when this is the case. So this is 0.95 collinearity, so they are nearly collinear. And I am showing here the different values of the parameter I want to estimate. But the point is that when you have, and all of these, each of these points, black points, are the solutions of the empirical risk minimization estimator. So just the standard sort of least square estimator. So the black one are the estimators obtained by least squares in each of these 100 experiments. And the red ones are the estimators obtained using distributionally robust optimization. So distributionally robust optimization, you can see that you introduce a little bit of bias, but you have a much nicer sort of like shrinkage properties. So they are not as wide, although you have sacrificed a bit of bias. So this distributionally robust optimization is also used as a technique to obtain estimators where you have to induce shrinkage in a principal way. Yes?
What is correlation here? Correlation among
this is the correlation among in the design matrix, in the factors of the design matrix. So you are running a linear regression, y equal to theta 1 x1 plus theta 2 x2, and so it's the correlation of x1 and x2. So this, one of these three papers that I wrote at the very beginning is a tutorial that will appear in Statistical Science that talks about statistical estimation and statistical robustness and distributionally robust optimization. And these are examples of different tasks that turn out to be equivalent to a distributionally robust formulation. So I haven't told you what it is, but you're going to see. It's going to be a game. It's a min-max game. And so, for example, this non-regularization like lasso, like a square root lasso, regularized logistic regression, that corresponds to a min-max game in which your adversary is designed using an optimal transport cost. Variance regularization, that's when you have like a loss and you want to penalize estimators that have high variance. That can be obtained using an uncertainty set that is called based on phi divergence. I'm going to tell you what phi divergence means. There is a notion that is called like adaptive boosting. So this is a way to kind of re-weight and you know, several sort of like estimators. That is part of is also part of distributionally robust optimization. Dropout training. That's a paper that that we wrote with my tocayo over there, you know, Jose Montiel there. So that's shows that that's a different type of DRO version, but this can be obtained. You know, there are many other sort of like tasks that can be made into direct one-to-one correspondence to distributionally robust optimization. And one thing that is very nice about DRO, as you're going to see, is that you not only obtain an estimator, but you obtain often a Nash equilibrium. So you have a notion of the least favorable distribution for your estimator within some range. So it has a very nice economics interpretation. When I've given talks in the statistics departments, they don't appreciate that too much, but in economics, I think they like this, yeah.
So just to the second example with the portfolio, for how many, so you had 20 stats, and how long was the training period for each?
10 years.
What was the frequency of
This was, I changed, yes, great. We did it for weekly and monthly.
I see.
And
so the issue is presumably not overfitting, it's some non-stationarity
the issue might be a non-stationarity.
Because if you run this and simulated data where there's no non-stationarity issue, presumably you do okay.
If you run this in data that doesn't exhibit sort of non-stationarity, maybe okay, I don't know. I think there is an issue of, definitely an issue of non-stationarity here.
Also, presumably, a large part of the non-stationarity is that a lot of people were actually solving this problem and trading upon that, and so.
Yeah, it could be right. It's hard to pinpoint exactly to what could be this.
But it seems to be a case where maybe the intuition is not so much regularization, penalization, but actually that there is a crazy distribution you need to protect yourself from. And
it could be the case, right? I mean, I don't. One of the nice things I would say, I would take that comment as a motivation for this distributionally robust optimization.
That's what I'm saying. I think because you have all these where you go to the rule and like, oh, there is a penalization, regularization, interpretation.
Right.
It seems like you're the primary interpretation.
Yeah. I mean, could be the case that correct. I mean, you can see that, for example, this design is not just another penalization. Turns out, and so you can get a little bit more bang for the buck with something that is just not a penalization. Now, so this is going to be clear when we talk about penalization here. It's going to be clear why penalization. Okay, just okay. So there is another type of. So remember, I told you before, like when you make decisions. The point is that the true distribution, which is the deployment distribution, is different from the distribution that you use to train your model. Okay, and so here is another situation like a little bit like that. It turns out that this actually is the same philosophy in robust statistics, but it has to do a lot with how the game. I always think in terms of a game formulation, in how the game is played. And which player moves first, okay? The statistician thinks about robustness in this way. They say, okay, you know, I have a theory that I can fit with data, but there is a point, this annoying point that I want to get rid of because it doesn't fit my data, and I think, you know, maybe it's contaminated, right? So I want to, you know, annoying thing, right? The contamination. So that's the way they kind of think about it. And the difference when you take this, you know, when you think about this problem is, okay, so what is it that is happening? You have some data generated distribution, you get some samples, you build an empirical measure if you are non-parametric, then you make a decision, and then you deploy, and then you have an out-of-sample distribution, right? And when we say that the true distribution is P, what we really mean is that this one here is equal to the one that you actually face when you deploy. Okay? It's very, very simple, very intuitive. Now, what the statisticians do is they think, well, this is my explanation, and when I explain it like this, when you do the math, it works very well. If you think that the contamination happens here, or the difference, right, the misspecification happens at the time of data collection or at the very beginning, or if you think that the difference happens at the time of deployment, so something is going to change the environment after you have made the decision, turns out that you get a different type of formulation. And so for the statistician, robust statistics is kind of, the statistician thinks that the data contains the truth. Somewhere inside the data there is the truth, and somebody has messed up the data when I got, contaminated the data. But inside there is the truth. And my job as a statistician is to kind of unravel the truth. And then, because then I'm going to face the truth, right? That's the P is equal to P star. In distribution and robust optimization, in this model, this example in finance, is more like, it's a situation where, well, your environment is probably going to change, or you don't have enough data relative to the complexity of your model. You have an ill-posed statistical problem where you need to leverage off, sparsity or something else. But for whatever reason, this thing here, right, in the end is different from this. That's the case where you have non-stationarities and you face something that is a different reality. Or you really have a problem where this is different from this, and you want to account for that in a way that maybe large sample asymptotics are not enough. Okay? So it's also a statistical question. It's also a statistical, task, but it's a different type of a statistical task than the robustness task. The robustness task is about something like this. So in robust, if you take the point of view of a game theoretic approach to kind of designing estimators, so the DRO approach is a situation where I'm going to make my decision, and then the adversary is going to come and is going to change the environment according to some distribution that is a perturbation of the data that I obtain. I have some notion of risk, and that's the game that we play when we use our hats of distributionally robust optimization sort of modelers. Okay? Yes?
So is the post-decision specification can also be interpreted as if we don't have a non-parametric model, but we have a parametric model, but we specify B, is it the same thing? Like, is this also the kind of specification?
This is, you mean you're talking about what is this B?
I mean, like,
Yeah, this thing here is this theta. The fact that comes here, it means that the mean is outside and the max is inside. I play first and then the adversary chooses. That's what I'm modeling here. This ball here I haven't talked about. Could be parametric or non-parametric.
I'm more asking about here we assume that PM is very close to P, right?
No, I didn't assume that. There is this is just a, I'm just telling you, at this point, I'm not talking about, you shouldn't make that assumption. Yeah, so all what you need to assume now at this moment is you have a notion of a model, could be a non-parametric sort of like empirical measure, it could be a parametric specification, whatever it is. That thing is going to be different from what you are going to see in deployment, and that's all what I'm saying. Yeah, and to address that mismatch, you could address that mismatch by playing this game. Okay? So that's it. And so we can talk about, in a minute I'm going to talk about this B. But the point is that when you have the misspecification happening here, the game you would be playing is this game. And if you have the misspecification coming in here, the game you would be playing is one where the max goes outside, right? So you get to see what the adversary has played, and then you need to do something. Okay, so now this is the sort of thing that Pepe has been talking about in the last few lectures, because for the statistician, this A, this capital A, is all the possible estimators. He needs to just figure it out, okay? He needs to figure it out how to clean the data, right? And if you think about somebody has done a max, a perturbation, right? So take a point, and it has moved the point, or take a likelihood, and has flipped the likelihood, has changed the likelihood. Maybe the likelihood of an outcome was a half, and now it become 2/3. Then the very most natural decision set of rules that you use to the data here is before you start solving the estimation problem for be it a mean, be it a linear regression parameter, you need to do another mean, the mean that actually kills this max. So if you know how the attacker is changing the data, you need to undo that data. So for somebody who has a hat of a statistician and wants to undo this max, he wants to first do a mean, which is a mean of this form. So the decision rule of a robust statistician is going to be something like minimize over some distribution that corrects the one that has been perturbed by the contaminator, and then after he does that, he then minimizes over the parameter according to some risk, right? So this is what is robust in statistics. This turns out, and I'm going to talk about that tomorrow, this turns out to be minimax optimal in a statistical sense, okay? So this stuff is completely opposite from this sort of thing. Yes?
So both these cases are basically, you have an empirical measure or some parametric,
Yeah.
right, and doing plug-in and making a decision.
Yeah, you plug in, so okay. When you, this is what you're describing is this approach. In this approach, you have, this could be the log likelihood, if you have that model, right? And then, you have the expected value under P once you take the logarithm of the likelihood if you have a parametric model. And then that's your loss, right? The negative of the likelihood. And you find this theta, and that's the plug-in estimate. That will be your estimate.